Hello, welcome to day 5 in our notes for Unit 13, Probability. Today's focus is going to be continuing our conversation on conditional probabilities and talking about the AND rule or multiplication rule for probabilities. Now, up until this point, we have been computing conditional probabilities solely using a two-way table by circling the column or row of the thing that's given and then dividing by a joint frequency, meaning a number from the middle of our table. Ultimately, this boils down to a formula. If you want to figure out the probability of A given B, it is always going to be the probability of the AND divided by the probability of whatever is given. So probability of events A and B occurring divided by, again, the probability of B because that's the thing that is given. Knowing this formula is helpful as it allows us to solve problems faster without needing to create an entire two-way table. So for example, of the light bulbs available at a store, 42% are fluorescent, 23% are labeled as long life, and 12% are fluorescent and long life. A light bulb will be selected at random from the light bulbs at the store. I want to find the probability that the selected light bulb is not fluorescent. And we'll state our answer as a decimal. So first of all, going back to just the things that I read in the problem that the probability of a fluorescent light bulb was 0.42, which is equivalent to 42%. Probability of being long life was 0.23, and then the probability of fluorescent and long life was 0.12 for 12%. Now, if they want the probability of not fluorescent, that's just got to be 1 minus the probability of them being fluorescent. So most of you guys can figure that out pretty quickly in your head. If there's a 42% chance of it being fluorescent, then there's a 58% chance of it not being fluorescent. And ultimately, that's just because I'm doing 1 minus 0.42. The selected light bulb is fluorescent given that it's labeled as long life. So this is what they're asking you to do. Probability of fluorescent given long life. Using my conditional formula, that's the probability of fluorescent and long life divided by probability of long life. Again, I'm just matching this. So they told me the probability of the AND was 0.12. Probability of long life was 0.23. And then it wants me to round to the nearest 1/10 of a percent. So I'm going to grab my calculator. Okay, so it's 0.5217 multiplied by 100. And that ends up being 52.2% for nearest 1/10 of a percent. So again, this conditional formula, which again is stated right up here, just makes this problem easier and quicker to solve because I don't need the entire two-way table. Let's set up the two-way table though, just to show you where this is all coming from. So the two things you're comparing are fluorescent and long life. So I'm going to set this up. 1, 2, 3. 1, 2, 3. I'll put fluorescent and not fluorescent. Long life, not long life. Okay. Now I'm going to do this out of 100%. That means fluorescent and long life, which was 12. So 12% will go right there. Probability of being fluorescent was 42%. Probability of being long life was 23. So out of 100, that's what each of those numbers would be. From there, I'm just filling in the table values that make sense. So like this would have to be 11 for those to add. This would have to be 30. Across here would have to be 77, and right here must be 58. which then makes this 47, because 47 plus 11 gives us 58. Now, notice how what we computed it be, so getting this 0.12 divided by 0.23 would be done using the table. So again, if I wanted the probability of fluorescent given long life, based on what you guys know so far from prior in this unit, I go to long life, circle that. So there's 23 light bulbs that are long life, 12 are fluorescent, so that gives me the probability of 12 out of 23, which again, if I do 12 divided by 23, it's ultimately going to end up being 52.2% again. Okay, and that's why that formula works. So it matches exactly what I computed up it be. All right, well, now that we have the table, find the probability that a selected light bulb is listed as long life given its fluorescent. So long life given fluorescent. So notice how I switched these. So that means given fluorescent. So now I'm going this way, and it's long life. Looks like 12. So that's 12 out of 42. It says state your answer in simplest fraction form. So I'll just grab my calculator here. 12 divided by 42, and I'll math frac that. 2/7. And that's your probability. Now, what I want to point out to you guys is that this probability right up here of F given L is not the same thing as L given F. So just note that it's not commutative. It's not like you can just switch those and get the same probability. The thing that changes is the denominator. That's your probability of being fluorescent, which matches this number right there, the 42. This is your probability of being long life, which matches how many long life bulbs there are. So again, it was always the intersection, the and, over whatever's given. All right, last question here. Find the probability that a light bulb is selected that is long life and not fluorescent. Okay, so I'll just put this in symbols to help us. Long life and not fluorescent. I go to long life, go to not fluorescent. Looks like it's 11. So that would be 11 out of 100 or 11%. And then we're done. And that just touches upon conditional probabilities. Now, if I ended right here, this would be the shortest lesson all year. So we're moving on to something a little bit different now, which is something you guys would have discussed in middle school, and it's the and probabilities with something called the fundamental counting principle. So let's suppose we're making a sandwich. You have two choices of bread, white or wheat, and then you have to select a meat. You have three choices, turkey, ham, or roast beef. I'm going to construct a tree diagram to represent all the possible sandwiches you could make. All right, so you get in line, you pick your bread. You got white or wheat as an option. So 2 options, 1 out of 2. From there, each of those bread selections has choices of meat of turkey, ham, or roast beef. So you could get white with turkey, white with ham, white with roast beef, wheat, turkey, wheat, ham, wheat, roast beef. So how many possible sandwiches can you make? Well, I count 1, 2, 3, 4, 5, 6. What is the probability of making a sandwich with wheat bread and turkey as a meat? Well, if I go to my tree diagram, picking wheat and picking turkey would be 1 out of my possible 6 options. So that would be 1/6. This probability can also be computed using something called the multiplication rule, which you guys are actually seeing right down here. This says that 4 events that are independent, so meaning they have no influence on each other, right? Me picking wheat had no influence on whether I was going to pick turkey. I can just multiply the probabilities together is what this is saying. So let's start with thinking about probability of selecting wheat. You had a 1 out of 2 chance of picking wheat. What was the probability of picking turkey? Well, you had 3 choices of meat and turkey was one of them. If you multiply 1/2 by 1/3, that is 1/6, which matches exactly the same thing I got from the tree diagram. So the point of this multiplication rule is it makes computing these more quick because I don't have to draw an entire tree diagram to do this. So suppose you're picking an outfit. You have 2 pairs of pants, and they say black or blue, 3 shirts, red, yellow, or green, and 2 pairs of shoes, white or brown. What's the probability you select an outfit with black pants, a red shirt, and white shoes? So again, you could draw a whole two-way table about this, two-way table, a whole tree diagram, or recognize that you have for pants 2 options, and black is just one of them. For shirts, you have 3 options, and red is one of them. And for shoes, you had 2 choices, which is then 1 out of 2 as well. Multiply that all together, that's 1 over 12, and that's the probability of selecting that outfit. So hopefully this seems pretty easy. This is stuff that you would have likely seen in middle school. Now here's where it gets a little bit tricky, because I'm going to talk about something called dependent events. So let's say you have a drawer full of 8 black socks and 4 white socks. So I'm already thinking, all right, you have 12 total socks in the drawer. What is the probability of selecting 1 black sock? Well, if you have 12 total in the drawer and 8 of them are black, there's an 8 out of 12 chance that you will pick a black sock. What is the probability you picked out a white sock, put it back, and then picked out a black sock? So again, out of your 12 total socks, 4 of them are white. Now, the idea that you took the sock and you put it back in the drawer means you are now picking from 12 socks again, right? Everybody's back in the drawer. What's the probability you picked a black sock next? Well, there are 8 black socks in the drawer. Multiply across, this would be 32 out of 144. Calculate the probability of reaching in twice for a sock and first selecting a black sock and then selecting another black sock. Assume you didn't put the first sock back in the drawer, and this is something called without replacement. So take this piece by piece. The first black sock, there's 12 total socks in the drawer and 8 are black. Now, the idea of you not putting the sock back in the drawer means that you're no longer picking from 12 socks in the drawer, you're picking from 11. Because there's 1 less sock in the drawer. Now, on top of that, if you're picking another black sock, keep in mind, you already put a black sock aside. So you don't have 8 black socks left in the drawer, you have 7. Multiply across the top and the bottom, and the probability would be 56 over 132. So this right here is what we did for dependent events. And what this means is we calculated the probability of the second event happening being adjusted because the first event happened. Okay, so technically I'm doing the probability of A times the probability of B given A, but truthfully I don't think about it so much as a formula. I just think about it in terms of piece by piece, what am I picking from, and coming up with a numerator and denominator as a result. So calculate the probability of reaching in twice for a sock and first selecting a black sock and then selecting a white sock. Assume you did not put the first sock back in the drawer. So again, 12 socks. First sock is black. Okay, now you're picking from 11 socks in the drawer. How many are white? Well, you didn't pick a white sock out to begin with, so that means all 4 of them are still left over. So this would be 32 out of 132. And that again is for dependent events because this probability was adjusted as a result of this happening first. This probability was adjusted as a result of this happening first. All right, last little bit we will do to get away from the drawer socks because there's only so many things I could do there is just touch upon a deck of cards. Some of you may be familiar with a deck of cards and some of you may not be. The idea is that there's 52 total cards in a deck, and there's 4 what we call suits. And the suits are what the pictures are on the cards. So clubs, spades, hearts, and diamonds. You'll notice half the deck is black and the other half is red. So hearts and diamonds are red, which kind of makes sense, hearts being red. Clubs and spades are black. There are 12 total face cards in the deck because those are the ones that have faces on them. So Jack, King, and Queen. And you also have 4 aces in the deck that just have an A on them. Now, don't worry if I ask you a question about a deck of cards on a quiz or a test, I'll give you a picture of a deck of cards so you don't have to have this necessarily memorized, okay? Although some of you probably do have it memorized. All right, let's calculate the probability of drawing 2 cards from a deck of 52 cards without replacement, meaning we don't put it back, and first getting an ace and then getting a face card. All right, so out of 52 cards, if you're going to pick an ace, there are 4 aces in a deck. Now, if you don't put the card back, that means you're going to be picking from 51 cards at your next selection. Now it wants you to get a face card. There are 12 options for face cards left over. 4 times 12 is 48. 52 times 51 is 2652. And that's your probability. All right, calculate the probability of drawing 2 cards from a deck of 52 cards, again without replacement, and first getting a 6 and then getting a jack. So again, out of those 52 cards, there are 4 that are 6s. Okay, now you don't put it back, so still picking out of now 51 cards, and then getting a jack. There are 4 jacks in the deck of cards. Multiply across the top and the bottom, and that's your probability. All right, last question of the lesson. Calculate the probability of drawing 2 cards from a deck of 52 with replacement. Oop, I changed the wording there, so now you're putting it back. And first getting a spade and then getting another spade. Okay, so 52 cards in the deck. Spades are a suit. This is 1/4 of 52, or 13 total cards. So 13 out of 52. Now, it's important to note that they said you put the card back because it says with replacement. So that means your second card selection is out of 52 again. And you put the spade back that you originally put back, so that means you're picking from 13 again. Multiply across the top and the bottom, and we would get 169 out of 2704. So these first 2 had some dependency to be aware of because you were not putting the card, or excuse me, you were not putting the card back. The last one was independent. These are 2 independent events because the second probability wasn't influenced by the first probability. And that is the and rule. So in summary, multiply probabilities together. Pay attention to basically whether you're putting the card or the sock back in the drawer. And your conditional rule, which you technically could always draw a 2-way table. It's just always quicker to know that the conditional rule is the probability of the and of the 2 events divided by whatever's given.